let's look at problem 1642, furthest building we can reach. For this problem, we're going to share a greedy method with the help of heap. First, I'll go through the statement of the problem, and then we will analyze the main idea and the procedure. And finally, we give the code and do a rigorous temp complexity analysis. So for this problem, actually the temp complexity analysis is what we want to convey most. So this problem, if we use the aid of heap, is not a very hard problem, I would say. So let's look at the statement of the problem. So we are given an integer array called heights, representing the heights of buildings, and some bricks and some landers. So the bricks and landers are our tools. So we start our journey from building 0 and move to the next building by possibly using bricks or landers when necessary. So while moving from building I to building I plus 1, so here the problem emphasizes that we use zero indexing. So first, if the current building's height is greater than or equal to the next building's height, we do not need a lander or bricks. So we can directly arrive at next building. So if the current building's height is less than the next building's height, we need either use one lander or this amount of bricks, that is the height of building I plus 1 minus the height of building I. So we are required to return the furthest building index we can reach if we use the given landers and bricks optimally. So that's the key, optimally, right? So it means that there are different strategies to use these landers and bricks. So here is a beautiful GIF. So example 1. So example 1, and so we can arrive at index 4. So here in the explanation, it provides a strategy. So we'll go over the details for this example later. So another two examples, one we can arrive at index 7, and the third one we can arrive at index 3. So here is very simple. From index 0 to 1, there's no need landers or bricks. And then from the index 1 to index 2, we need 16 bricks, and then 19 is higher than 3, then we can directly up to this index 3. So that's about the examples. Now let's look at the constraint. So basically the constraint, the first item is important, which said that the height can have a length up to 10 to the power 5th. So in other words, we cannot tackle this problem purely by brute force. The second and third constraints are about the range of heights and bricks. And the last one is basically for consistency. For example, landers should be less or equal than the heights of the length of the heights. Otherwise, we can directly arrive at the last index. Just use a lander at each jump if necessary, right? So that's the analysis of the problem. So now let's look at the method and the procedure. So here the method is a greedy method. So with the help of the heap abstract data structure. So the idea actually is very simple. So at each index I, so we use bricks whenever necessary and possible. Necessary means we need a jump, and possible means that we have enough bricks. And if not possible, we are going to find the largest jump till now and use a lander to fill in that gap and update the number of bricks if necessary and accordingly. So that's the main idea. So here, maybe wondering, so how do we determine which of the jumps we need to use lander? So here, because we do this at each index, we automatically do the right thing. So the key point is that, so for the check of the largest gap or gaps so far, so we need the help of data structure. So here we are using a heap. So now with that covered, let's look at a example and look at the procedure. So here is example 1. So it's the height, this is the corresponding index, and the current state of bricks and landers. So the specific procedure is as follows. So we initialize a heap to easily track the largest jumps. So then we start from index 1, because originally we are at index 0. So at index 1, we check if we need a jump. So we check the current height minus the previous height. If it's less than 0, it means the previous height is higher than the current one. So we can directly arrive at this index from the previous one. So the state does not change and the heap is empty. Then we continue to next index. So for the second index, we check the difference again. So 7 minus 2 is 5, means that we need a real jump of size 5 from the previous one to the current one. So now we have 5 bricks, and which is greater or equal than the differ. So we try to use 5 bricks here. So we update the number of bricks by 5 minus difference, that is 0 now. And then we push the current jump into the heap. So here notice that we are trying to use a min heap. So we put a negative the difference here. The reason is that later if we pop the most negative one, then we put a negative sign, we will get the largest gap. So this is the index 2. So after index 2, we have bricks 0, and we have lander 1, and the heap is negative 5. So at index 3, we check the difference of height. So 6 minus 7 is negative 1. So it means that we do not need to jump to arrive at this index. So the bricks is 0, lander is 1, and heap is negative 5. So we continue. So up to this index 4, this is the point we need some thought. So here the differ is 9 minus 6, that is 3. So we need a jump. So now the bricks is 0, so which is less than the current depth. So we need to consider to use lander if available. So now we need to use one lander, but we do not use the one lander for the current jump, but we use one lander for the largest jump so far. So now we pop from the heap to get the largest jump up to this index, that is negative 5, then put a negative, that is 5. So for the largest jump, we had used the bricks before, but now we change to use a lander instead, so that we can have most bricks after using one lander. So well, for the current jump, we still try to use bricks, as specified by our main idea. So the bricks now is updated like this. We have 0, and then we return the 5 bricks we used for the largest jump, and then use 3 of them for the current jump. So we have 2 bricks now, and the landers will decrement by 1 because we use one lander for the largest jump so far. So the heap, actually we pop the negative 5 and then put the negative of the current jump, that is negative 3. So that's the current state of the heap. Then let's examine the next index, that is index I equals 5. So 5, the diff is 14 minus 9, that is 5. But now we do not have enough bricks. So the bricks we have is 2, which is less than 5. We need to try to use lander. So but we do not have any lander now, so we cannot arrive this index. So we are going to return the previous index, in other words I minus 1, which is 4. So that's a full analysis of example 1. So you can look at the GIF again. It's sort of beautiful. So now before we look at the code, let's make a challenge. So can you run the above procedure for example 2? So I would say this will be very routine. So now let's look at the code. For the code, basically I will just verbally translate this into code. First, for this purpose, I'm going to track the length information for the heights. So now this I also initialize a heap for the track of largest gap. So this is step 1. Let's call it preparation. Now step 2, the real work. For the real work, basically we just write up the above logic. So this is actually simple. So we start from index 1, so for range 1 to n. Then we consider the jump or difference, which is def equals the current height, that is height I, minus the previous one, so that is I minus 1. So we want to check the sign of this one to determine if we need bricks or landers. So if diff is less than 0, we do nothing, right? If it's greater than 0, so we do some work. So first we will try to use bricks. So if bricks is greater or equal than diff, it means we have sufficient bricks. So we use bricks now, for now, temporarily. So we decrement by diff, and then we use this library heap, or use heap push. I'll push the heap name and the diff. So again, I'm put a negative so that I'm actually using min heap. When I pop the element, we'll get the most negative one. Then I add a negative sign, I will get the largest jump. So that's the first case, if bricks is sufficient. Otherwise, we try to use a lander. So if the landers equal 0, so in other words, we do not have any landers, so we just need to return I minus 1. In other words, we cannot return building I, so we return the I minus 1. So otherwise, if we have landers, we need to use the landers for the largest jump. So let's call it maximum. So the maximum jump. So this is heap q heap. So I will do it in one go, heap pop. So I will pop the largest one, and also I will put the diff negative, right? So this is the largest jump, but notice that we need to put a negative sign as we emphasized before. So now with this, so we want to update the bricks. So the bricks will be, I will add back the maximum, right? And then I will use the bricks for the current jump, that is diff. So the overall result is that we increment bricks by maximum minus diff. So that's about this main step. Also, we need to decrement the number of landers by 1 because we are using 1 landers. So that's about it. So in the process, we should have returned something. If not, meaning that we're going to get to the last building. So that's basically the full code. So first we did some preparation, and then we do the real work by considering if we can use the landers first, then we consider, or if we can use the bricks first, then we consider using the lander. So that's it. Let's test the special case. Yeah, it passes the special case. Here, let me print out the state of at each index. So at index I, so what's the state of the bricks? So and the landers, and what's the heap? Just for this special example. So now this is the bricks, landers, and heap. So you can consider here. So a bricks 5 1 empty, and last state we have 2 0 negative 3. So that's it. Let me comment this out. So and test the generic case. Yeah, it passes the generic case. So now let's do a actual point. Up to now, basically, we can end, but for this problem, we want to do a temp complexity analysis. So, but this is sort of interesting. So at each step, So we need to basically do what we want to do is the most time consuming one is check the smallest element in the heap, then do the pop. So that operation is O of log I, right, at each step. So it's bounded above by this operation. So overall temp complexity will be log 1 plus log 2 plus log up to n, right? But this is nothing but log 1 times 2 times up to n. In other words, this is nothing but log n factorial. So now I think it might remain you something interesting. It's called Stirling's formula. So basically it says that log n factorial equals, or roughly when n tends to infinity, log n times log n minus n plus 1 or something, but it's the same thing. So overall, this is O n times log n. In other words, the time complexity of this algorithm will be this guy. And the space complexity, so it's simple. So space complexity will be O of n, because the size of the heap is bounded by the length of the height. So with that said, I guess that's about it for this video. It's sort of longer than previous ones. Thank you very much.